Okay, Assalamualaikum everyone. This is a recorded topics for change of variable, okay, and surface area. Okay, so this change of variable is a continuous topic from our class last week, okay. So the change of variable is on page 189, okay. The concept in changing the variables will be based on this integral. So I'm going to read the integration for f gx and its derivative of gx with respect to x variable. Okay, for AB will be equivalent to fu du for the integral between c to d, whereby we have u is equal to a function of g in terms of x. Okay, so this one u equal to gx here is the change of variable. Okay, so we have here one function that is we change it, but we may apply the same thing if we have two functions. Okay, so for simplification, we may assume that this as the coordinate system. Okay, so you have learned the coordinate system in polar, in cylindrical, or in spherical. So the change of variable can be represented by their coordinate system basically. Okay, so we will go directly to the example, but before we start with the change of variable, there is a there is a special methods that apply for implementing the change of variable that is based on Jacobian transformation. Okay, Jacobian transformation. Okay, so in this slide, the Jacobian of the transformation, when we have x equal to GUV, okay, so this must be assumed as the function in term of G, function G. There are two variables UV. Then we have another y expression that is equal to function H that is in terms of UV. So we may evaluate their determinant as follows. Okay. So this symbol refers to the partial derivative of x, y with respect to UV. So the one on the right hand side here we call determinant. Okay, so this determinant you have seen the symbol in engineering maths 1, how we find the determinant for the matrix. Okay, so here we have the terms in terms of partial fractions. Okay, so means that we have the x just now, we differentiate with respect to u. So this is the first part. Then on the another one, we have x just now, we differentiate with respect to v. Okay, and therefore y, we differentiate y with respect to the first variable u. And the last part, we differentiate y with respect to the second variable that is v. Okay, so we are supposed to find the partial derivative and then find the product between the two diagonal entries. If we have this kind of determinant, when we expand it into the partial derivative, so this is the expansion. Okay, so it is a product between x that we differentiate with respect to u times product of derivative y with respect to v, okay, and minus differentiate x with respect to v times differentiate y and then differentiate with respect to u. Okay, so this is the one that we'll be using in our change of variable for a double integral. Okay, so in the double integral, the change of variable will be as follow. Suppose that we want to integrate the function fxy over the region R under the transformation for x and y as follow. So the region becomes new region S and the integral becomes like this. Okay, so the one on the right hand side is the new integral. Okay, we'll see example 3. for this change of variable problems. Okay, we have, so in example 3, the problem is to evaluate the double integrals given here, dA, where R is the trapezoidal region with vertices given by the points. This is the first point, second point, third point, and the last point, using the transformation X and Y here. Okay, so first thing, we sketch the region as follow. Okay, we mark the points and we draw the straight line. And then we determine the equation. Okay, the straight line, the red line here. So this is the equation. How you can find the equation? You can use y equal to mx plus c. So we have some pairs of coordinates here. So you can substitute and we have here, this is the straight line equation for the red line. Okay, so for the blue line, the equation is y equal to x. For the yellow line, the equation is y equal to negative x. For the blue line, we have y equal to x minus 5. Okay, so once we determine the straight line equation for the region, okay, and then we are going to use the transformation given in the question just now. Okay, so we start from the yellow line. Okay, so this is the transformation. We have x and y. Okay, so when we have y equal to negative x, so this equation y equal to negative x must be transformed into the one containing u and v. Okay, so we put it here. So y on the left hand side, y is 2u minus 3v. So on the left. On the right, we have negative. So in the brackets, 2u plus 3v. So we have one equation for the yellow line. So we are doing the same thing. For y equal to x, for y equal to negative x plus 5, and also for the blue line here. Okay, so for the first equation, y equal to x, we have left hand side and right hand side using the transformation. Then we have v equal to 0. Okay, for y equal to negative x, we do similarly. So this is transformation by changing the variable. So we have u equal to 0. Okay, so the next line, we have this equation. Okay, transform it into a new variable in terms of u and v. Then we have this equation, u equal to 5 over 4. Then we do last one, y equal to x minus 5. Then we have v equal to 5 over 6. Okay, so the new region will be the region bounded by these 4. Okay, so we have u0, v0, e equal to 5 over 4, v equal to 5 over 6. And then we have the range basically. Okay, so u is from 0 to 5 over 4. And v is from 0 to 5 over 6. So we have range of u and v. Okay, so before we applying the change of variable in this theorem, okay, so remember they were supposed to evaluate the determinant. Okay, so we are doing similarly here. We need to find the determinant. Okay, so from our transformation in the question, this x equal to 2u plus 3v. First one, find the partial derivative as shown here. Okay, so we have x equal to 2u plus 3. Okay, we are using partial derivative. Okay, so this is partial derivative. We differentiate this x with respect to u. Differentiates. So this 3v will be assumed as the constant. We have 2. Then we have to differentiate x with respect to v. Then we have 3. Okay, for y we do similarly. So y we do find the partial derivative of y with respect to u. Then we have 2. So other part will be assumed as a constant. Then differentiate y with respect to v. Then we have negative 3. Okay, so when we put into the determinant form, we have here these 2. It is here. Okay, this is 2 that is comes from this, the partial derivative of x with respect to u, and we have here 3. This is partial derivative for x with respect to v. And then we have here that is 2, and we have negative 3. This 2, put it here, and this negative 3. Okay, so find the product between the diagonal. So we have negative 6 minus 6. So we have negative 12. Okay, so the middle one supposedly negative. Okay, next we substitute everything here into our double integral. This is double integral in the Cartesian xy. So everything will be converted into a new transformation, okay, in terms of u and v as follow. This is x plus this is y. Okay, times with the determinant. Okay, times with determinant. So the value of the determinant must be negative. Absolute of negative. Okay, this is actually absolute value. Absolute of the determinant. Okay, so we have here negative 12. So when we put absolute symbol, this part must be positive. Okay, and then we have du dv. So this will be limit for u. This will be the limit for v. Okay, so we expand the bracket. So we have for u only. Okay, but there is a 12. So 4 times 12 will be equal to 48. Okay, so we simplify first before we start the first integration with respect to u. Okay, so this direct integration will be 48u squared over 2. Simplify 48 with 2, then we have 24u squared. Okay, and then substitute the value when our u is equal to 5 over 4 and u is equal to 0. Okay, so you can use your calculator, we will get this part. And then we do integration, the last part with respect to v variable. Then we have this v. And then substitute when our v equal to 5 over 6 and when v is equal to 0. Simplify, and this is the simplest part that we get that as 1 to 5 over 4. Okay, example 5, this is actually proving problems. Verify that our dv that is equal to rho squared sine phi d rho d theta d phi. So problem 5 actually is to prove. Okay, so we are supposed to use change of variable in spherical. Okay, spherical into Cartesian in 3D. Okay, this is a transformation. So if you are not sure where this formula comes from, then please refer to your sample final exam. Okay, and also in the ebook there is a transformation formula from spherical to Cartesian like given here. Okay, so we have x, y, z. So each part of this will be differentiated according to the different variables. Okay, so in spherical, we have phi, theta, we have in spherical coordinates, we have rho, theta, phi. Okay, as shown here, rho, theta, phi. This in spherical. So please take note about the uh, arrangement for the variable. So x, y, z is in the Cartesian 3D. So rho, theta, phi is in the spherical. Okay, so using this x, okay, this is x transformation. So this x, we have to differentiate with respect to rho. First variable is rho. Okay, so differentiate rho. So we have sine phi cos theta, let's say here. Okay, so first variable, this is actually the partial derivative for x with respect to rho. So we get here. This is partial derivative for x with respect rho sine phi cos theta. Okay, so when we want to differentiate with respect to rho, so sine phi and cos theta will be assumed as the constant. Okay, so constant. So that's why we got here as the constant only. Okay, so with the same transformation x, now we proceed differentiate with respect to theta. So this part will be assumed, these two will be assumed as a constant. So differentiate cos theta, we have negative sine theta. That's why we have here negative rho sine phi sine theta. So this negative comes from the derivative of cos theta. Okay, next this is partial derivative for x with respect to phi. Okay, so we have sine phi, differentiate sine phi, we get cos phi. Okay, so the next row, this is actually derivative for y with respect to phi. This is derivative for y with respect to theta. This is derivative for y with respect to phi. Okay, this is derivative for z with respect to rho. So we have here, okay, look at. Then this derivative for z with respect to theta. We don't have theta here. That's why when we differentiate with respect to theta, it becomes 0. This is derivative for z with respect to phi. Okay, so differentiate cos phi, we have negative sine phi. That's why we have here negative rho sine phi with the assumption rho is the constant. Okay, now we have actually the derivative between 3 by 3 rows. So you can find using the product between the elements in the matrix. Okay, so the expansion will be given here. So we got this one. Okay, so I hope you still know how to find the determinant for 3 by 3. Okay, so if you uh, do not remember, so please recall back. Okay. Okay, so this is the simplification for the determinant. We'll get this one. Negative rho squared sine phi. Okay, so the next step is to substitute into the change of variable for the for the triple integral. Okay, so the triple integral, so we have here dv. This is actually our determinant. So we just times out with our d rho d theta d phi. Okay, so once we determine the determinant, we put it into the dv. So dv, remember, dv in the Cartesian 3D will be equivalent to this one. So we need to multiply with determinant, absolute of the determinant. This is actually our determinant, but we have to evaluate the positive value only. Okay, that's why we implement the absolute here. So this is actually supposed to be rho squared sine phi. Okay, then it will be equal to rho squared sine phi d rho d theta d phi. So we got the answer for the proving. So this now is a So this dv is now equivalent. The left hand side is equal to the right hand side. So this answer our proving problem. Okay, so we are going to continue on double integral and we will see the example on surface integral. Okay, so the change of variable, that is the first subtopic for the recorded class. So we are going to see the surface area. Okay, so this surface area actually is the application for the double integral. So the formulation for the surface integral is shown in this box. S refer to the surface area that is equivalent to the double integral over region D, then square root of fx squared plus fy squared plus 1 dA. So fx means that we have the function for f in terms of two variables. We differentiate that function f with respect to the first variable. And fy refer to the function and we differentiate the function with respect to the second variable. Okay, so if our function is z equal to fxy, so the first variable is x, second variable is y. So please adapt when the function of z equal to fxy is changed to other notation. Okay, so for this surface area, we will see example 1. find the surface area of the part of the plane 3x plus 2y plus z equal to 6 that lies in the first octant. Okay, so when state as the first octant, actually it's referred to a solid that in the first quadrant. Okay, find the surface area of the part of the plane 3x plus 2y plus z equal to 6 that lies in the first octant. So first octant refer to a solid that lies in the first quadrant. Okay, so we call it as the first octant. So the straight line equation is here, 3x plus 2y plus z. So we can figure out the figure for the straight line equation between the three axes x, y, and z, like this figure. Okay, so how we get 6, how do we get 2 and 3? We can let one of the axes non-zero and the other two axes let it equal to 0, so we will get the solution at one of the axes. Okay, so this is z equal to 6 when our x and y 0. This is y equal to 3 when our x and z 0. This is x equal to 2 when we have y and z axis as 0. Okay, so this is actually the figure of the solid in the first octant. Okay, so basically this is the first octant. That is the first quadrant lies between the three axes. Okay, we are interested, okay, to look at the region between xy plane because we are going to find out what is the limit for x and y. Okay, so from this straight line equation, we can express z. Okay, for example, so with z here will be 6 minus 3x minus 2y. So basically, this is our function in terms of f xy. Okay, so next, before we find the double integral, we are supposed to look at the x and y plane and find out what is the limit. Okay, so between the xy plane, okay, this xy plane is actually, we have this equation, straight line equation between 3 and 2. Okay, so when we figure out two-dimensional, we have this kind of region. Okay, so the straight line equation for y3 and x2 is here. Okay, we can find out by using y equal to mx plus c. So the gradient is 3 over 2. C is the intersection at y-axis. So this is the value of c. Okay, so we have this straight line equation. Okay, so when we have to perform or to evaluate the double integral for the surface integral, we are supposed to find out what is the limit of x and y, and then we have to make sure whether we are going to use dy dx or dx dy, okay, in the double integral. Okay, so for the x-axis, in this figure, we can refer to this point, the origin x0 and x2. So we have fixed limit of x. So the lower limit is 0. The upper limit is 2. Okay, for y-axis, we have y0 to this closed region that is bounded by the straight line equation. So the lower limit for y-axis is 0, but the upper limit is not a fixed value. We have upper function, okay, that is being represented by this equation. Okay, so this is actually the upper function for y-axis. Okay, because of that, our x-axis contain fixed limit. Okay, so the double integral that we are supposed to use here is dy dx, not dx dy. Okay. So when we substitute into the double integral in the surface formulations, okay, surface area is equal to double integral for fx squared plus fy squared plus 1. Okay, so fx squared, so remember that we have this z equation. Okay, so this is fxy. Differentiate this equation with respect to x. So the 6 and negative 2y will be assumed as the constant. So differentiate this part only. So we have negative 3. With the same function here, we are supposed to evaluate the derivative with respect to y. Okay, so this 6 minus 3x will be assumed as the constant. So differentiate negative 2y, we have negative 2. So once we find what is fx and what is fy, we put it into the formulation here. So this is fx squared plus fy squared. So expand the bracket. So here we have 9, then we have 4. Okay, 9, 4, 1. So the summation is 14, then we have square root of 14. So this dA is the symbol in the Cartesian. Then we put it detail dy dx. So we have dy here from 0 to the upper function. X-axis from 0 to 1, from 0 to 2. Okay, so this limit we already identified just now. Okay, and then we can perform direct integration. First is to integrate with respect to y. Then we have square root of 14y. Substitute when y is here and y 0. So we get this part. Okay, and then from this part, we are supposed to integrate with respect to x. So this becomes x squared over 2 combined with this number. Then 3 here becomes 3x. Okay, so finally, we evaluate the definite integral when x is equal to 2, when x equal to 0. Okay, put it here. So when x0 is 0, so we just need to evaluate for x2. Okay, then we have the final number as 3 and square root of 14. So you can leave it in terms of square root of 14, or you can express the number in decimal point. Okay, so that is the example 1. Okay, for example 2, I'm not going to explain because the problem actually is very simple. So for this example 2, I want you to study by yourself. Okay.